And let capital C be the straight line segment from point A 0, comma 2, comma 1 to point B 4, comma 1, comma minus 1. What is the value of L? So let us understand the given question. So we are going to find what is answer for a given single integration, and it is represented as L. And the variables are real. All the three variables x, y, z are real. And given what is the curve, in which curve we are evaluating the given single integration. So it is evaluated over the curve capital C. Capital C is nothing but a line segment from the point 0, comma 2, comma 1 to the point 4, comma 1, comma minus 1. Now let us see how we are going to work out this problem. So this problem is taken from vector calculus. So first of all, let me find out what is the equation of the line segment which connects the point 0, comma 2, comma 1 to 4, comma 1, comma minus 1. Let us have a diagram. So I'm drawing a line segment and I'm marking the left end point as capital A 0, comma 2, comma 1, and the right end of the line segment capital B 4, comma 1, comma minus 1. And for notation sake, I'm calling the coordinates of point A as x1, y1, z1, and the coordinates of point B x2, y2, z2. Now we know that AB is a line segment. So we are going to find what is the equation of the line AB. And we know that equation of line AB is given by the formula x minus x1 divided by x2 minus x1 equals y minus y1 divided by y2 minus y1 equals z minus z1 by z2 minus z1. Now we are going to substitute what is your x1 value, x2 value, y1 value, y2 value, z1 value, and z2 value in the above formula, right? So therefore, the above formula becomes x minus x1 value is 0 divided by x2. x2 value is 4 minus x1 value is 0 equals y minus y1 value is 2 divided by y2 1 minus y1. y1 value is 2 equals z minus z1. z1 is 1 divided by z2 minus z1, which is minus 1 minus 1. Now we can simplify the proportional values. X minus 0 is x, 4 minus 0 is 4. So x by 4 equals y minus 2 divided by 1 minus 2 is minus 1. So I have y minus 2 by minus 1 equals z minus 1 by minus 1, which is minus 2. Now these three values are proportional. So let me call the values are equal to t. Now you take x by 4 and equate with the t. So from this we get x equals 4t. Next, y minus 2 by minus 1 equals t. So from this, your y minus 2 is minus t, or I can say y value is minus t plus 2. And finally, z minus 1 by minus 2 equals t. So from this, your z minus 1 value is minus 2t, or z value is 1 minus 2t. So the idea is the given integration is single integration. So we are going to convert all the three variable into a single parameter. And the parameter we are going to use is t. Now we are able to got relation between x in terms of t, y in terms of t, and z in terms of t. Now let us find what is dx, what is dy, and what is dz. So x is 4t, so your dx will be 4 times of dt. Y is 2 minus t, differentiate on both sides. So y becomes a dy, 2 becomes 0, minus t becomes minus dt. So dy value is minus dt. And finally, z equals 1 minus 2t. You differentiate on both sides. Z becomes dz. 1 becomes 0. Minus 2, t becomes dt. So your dz value is minus 2 into dt. So now we converted all the three variable x, y, z into a single parameter t. And now let us find what will be limit of the new parameter t. Okay, to find limit of t, I'm going to take limit of any one of the variable. So let me take a limit of x. So from the point A, your x coordinate is 0. Point B, x coordinate is 4. So lower limit of x is 0. Upper limit of x is 4. Now you use x and t relation. So what is the relation between x and t? X equals 4t. Substitute x value as 0. Your y value, t value is also 0. Now substitute x value as 4. Your t value becomes 1. So therefore, I am able to get limits for the new parameter t. Lower limit is 0, upper limit is 1. So therefore, I'm going to substitute all these limits and relation connecting x in terms of t, y in terms of t, z in terms of t in the given integration L. So therefore, the given integration becomes integration between 0 to 1, 2 times of z value is 1 minus 2t into dx. What is dx? It is going to be 4 times of dt plus second term 2y dy. 2 into y value is 2 minus t and dy value is minus dt plus third term 2x dz. 2 into x is 4t, dz is minus 2 into dt. Now we are going to simplify all the terms inside the integration 0 to 1. So 2 into 1 into 4, which is 8. And 2 into minus 2 into 4, which is minus 16t. And next one, 2 into 2 into minus 1 is minus 4. 2 into minus t into minus is plus 2t. And then 2 into 4 into minus 2 is minus 16t. Now we can simplify all the like terms inside the integration. So we have minus 16t, which is minus 32t and plus 2t. So totally it gives me minus 30t. And then constant 8 minus 4 gives me plus 4. So integration 0 to 1, 4 minus 30t dt. Now we can integrate term by term. So first term, there is no t term. So after integration, you just multiply by t. So 4 into t minus second term t. Integration of t becomes t square by 2. So that t square by 2. Now we can cancel 30 and 2. So your numerator becomes 15. Apply the limit. So first of all, we apply the upper limit. That is, we are going to replace all the t value by the upper limit 1. So therefore, I'm going to get 4 minus 15 minus replace all the t values by 0. So you're going to get 0. So 4 minus 15. So the final answer is minus 11. So therefore, the answer for the given single integration L is going to be minus 11. Hope you understand. So coming to the next problem. Suppose capital C is the closed curve defined as the circle x square plus y square equals 1 with the capital C oriented anti-clockwise. The value of integration over C x y square dx plus x square y dy over the curve C equals what? So here we have to understand the problem. So given single integration and the integration is taken over a closed curve. That is very important. The integration is taken over a closed curve and the direction of the or orientation of the closed curve is anti-clockwise. So usually we take anti-clockwise direction as positive direction, right? So now we are going to find answer for the integration over the closed curve, single integration over closed curve using Green's theorem. Because the curve is closed, so we can imply or we can appeal Green's theorem. So let us recall our Green's theorem. So the Green's theorem says integration over C, that is closed integral over C, u dx plus v dy equals double integral over v over r dou v by dou x minus dou u by dou y into dx dy. Now, the given question is going to be left-hand side of the Green's theorem. So, you are going to find what is the answer for the left-hand side using the right-hand side. Okay. Now, let us compare the given single integration with u dx plus v dy. So, in the place of u, I have xy square. So, u is nothing but coefficient of dx in the single integration. And v is coefficient of dy in the single integration, so which is x square y. So now from u, you find out dou u by dou y. So differentiate u partially with respect to y. So u is xy square. So when I differentiate u partially with respect to y, x is constant, right? So y square becomes 2y. So the final answer for dou u by dou y is 2 times of xy. Next, v is given. We want to find dou v by dou x. That is, differentiate v with respect to x partially. So when I differentiate v with respect to x partially, y is constant. So x square becomes y. Now we can make use of these partial derivatives to find answer for the single integration. So by Green's theorem, integration over C xy square dx plus x square y dy equals double integral over R. So substitute dou v by dou x. So dou v by dou x is 2xy minus dou u by dou y. Dou u by dou y is also 2xy into dx dy. So 2xy minus 2xy is 0. We know that integration of 0 is going to be 0. So therefore, the answer for the given single integration is 0. Let us move to the fourth equation. The magnitude of the gradient for the function f of x comma y comma z equals x square plus 3y square plus z cube at the point 1 comma 1 comma 1 is what? So in this problem, we are going to find what is the magnitude of the gradient for the given surface. So what is the surface given? It is f of x comma y comma z equals x square plus 3y square plus z cube. And we are going to calculate gradient at the point 1 comma 1 comma. Now let us find what is gradient first. So after finding gradient, we can go for magnitude. So please remember, a gradient is a vector quantity. So the answer will be a vector. Now let us recall what is formula to find a gradient of a function f. The gradient of f is given by del f. So the notation for gradient is del f. Inverted triangle symbol, we should read it as del. Del f, where del represents a vector differential operator I vector dou by dou x plus j vector dou by dou y plus k vector dou by dou z. Now let us write what is del f. So del f is going to be I vector dou by dou x plus j vector dou by dou y plus k vector dou by dou z, and given f is x square plus 3y square plus z cube. Now we can do the normal multiplication. It is going to be I vector dou by dou x of x square plus 3y square plus z cube plus j vector dou by dou y of x square plus 3y square plus z cube plus k vector dou by dou z of x square plus 3y square plus z cube. Now we can simplify the components one by one. So I vector dou by dou x of x square plus y 3y square plus z cube. That is, we are going to differentiate partially with respect to x. So we have three terms. So out of the three terms, second term and third term are constant when I differentiate with respect to x partially. So therefore, second and third term contribute 0 to the partial derivative. And the first term x square becomes 2x. So therefore, I'm able to get what is my ith component of gradient of f, which is a 2x. Coming to the jth component. So jth component of del f is dou by dou y of x square plus 3y square plus z cube. Again, we are going to differentiate partially with respect to y. So if you look at the first term and the third term, there is no y term, or I can say they are constant. So it becomes, so it becomes, so it becomes 0. So the second term, 3y square, when I differentiate partially with respect to y, it becomes 6y. So therefore, I am able to get what is my jth component of del f. So jth component of del f is going to be 6 times of y. And coming to the kth component is dou by dou z of x square plus 3y square plus z cube. Again, differentiate partially with respect to z. First term and the second term are constant. Third term, z cube becomes 3z square. So therefore, the kth component of the gradient f is 3z square. Now we are going for a gradient at the point 1 comma 1 comma 1. So therefore, in the above gradient value, we are going to replace x value by 1, y value by 1, and z value by 1. So therefore, your ith component becomes a 2, and jth component becomes 6, and the kth component becomes 3. So therefore, your gradient of f is 2i plus 6j plus 3k. But what is our actual equation? Magnitude of gradient. So what is magnitude? For a vector, you just find modulus. So magnitude of the gradient is modulus of del f, which is given by root of 2 square plus 6 square plus 3 square. Ith component square plus jth component square plus kth component square, which gives me root of 4 plus 36 plus 99. So which gives me root 49. So root 49 is 7. So therefore, we are able to find the gradient of the given function f at the given point 1 comma 1 comma 1. That is, the magnitude is 7. Let us move to the fifth problem. So the directional derivative of f of x comma y equals x y by root 2 into x plus y at 1 comma 1 in the direction of the unit vector at an angle of pi by 4 with y axis is given by what? So we are going to find the directional derivative. But here the information was not directly given. So we are going to collect all the information from the given question. So first of all, the direction vector is given. Okay, the direction vector is a unit vector. It is not directly given, but it is given using some condition. Using the condition, we are going to find what is the directional vector action. Direction of the unit vector at an angle of pi by 4 with y-axis. So let us find this. So the unit vector at an angle of pi by 4 with y-axis is given by n cap equals pi by 4 is nothing but 45. So the unit vector is given by n cap equals cos 45 I vector plus sin 45 j vector. We know cos 45 is 1 by root 2. Sin 45 is also 1 by root 2. So therefore, the unit vector is going to be 1 by root 2 into I vector plus 1 by root 2 into j vector. If you want, you can take the common factor 1 by root 2 outside. So 1 by root 2 multiplied by I plus j vector. Now let us find what is modulus of this unit vector. So since it is a unit vector, its modulus is going to be 1. So modulus of n cap is 1. Now let us find directional derivative. So what is formula for directional derivative? It is given by del f dot n cap. Del f is given by I vector dou by dou x of f vector xy by root 2 into x plus y plus j vector dou by dou y of f xy by root 2 into x plus y. So it is a two-dimensional vector. So we have only I and j. Now we can simplify the components of del f, gradient of f. So when I differentiate with respect to x, before doing differentiation, you just simplify the terms. So you'll get I by root 2 dou by dou x of xy into x plus y, which gives me x square y plus xy square. And then coming to the jth component, j vector by root 2 dou by dou y of, again you multiply xy with x plus y. You are going to get x square y plus xy square. Now you can do the differentiation and simplify the components of gradient of f. So dou by dou x of x square y plus xy square, it becomes 2xy plus y square. Second one, jth component, differentiation of x square y plus xy square partially with respect to y, it becomes x square plus 2xy. Now we are looking for gradient at the point 1 comma 1. So that is, you replace x value by 1 and y value by 1 in the above answer. So therefore, you are going to get 1 by root 2 into 2 into 1 into 1 plus 1. So 2 plus 1 is 3. 3 by root 2 into I vector. And then jth component. So it is 1 by root 2 into 1 square plus 2 into 1 into 1. So which is 3 by root 2. 3 by root 2 into j vector. Now using this gradient f and n cap, we can able to find the directional derivative. So the directional derivative is given by del f dot n cap. Substitute del f and n cap. So del f vector, del f is 3 by root 2 into I vector, 3 by root 2 into j vector dot n cap is 1 by root 2 into I vector plus 1 by root 2 into j vector. Now we are multiplying two vectors, that is del f and n cap, using dot product. And when I do vector multiplication using dot product, I should multiply component wise. That is, ith component of the first vector is multiplied with ith component, the jth component of the first vector is multiplied with the jth component of the second vector, etc. So therefore, I'm going to get 3 by root 2 into 1 by root 2, which on simplification gives 3 by 2. And then again, kth component, 3 by root 2 into 1 by root 2. On simplification, it gives me 3 by 2. So 3 by 2 plus 3 by 2 is nothing but 6 by 2. So 6 by 2 on simplification gives me 3. So therefore, the required directional derivative is 3. Hope you understood the last problem. Now let us continue our class with the next problem. Excuse me. Yes, let us solve one more problem from vector calculus. If the vector field F equals A suffix x into 4y minus c1z plus A suffix y, 4x plus 2z plus A suffix z, 2y plus z in a rectangular coordinate system x comma y comma z with unit vectors ax comma ay comma az is irrotational, then find the constant c1. Okay, so now a vector is given, and instead of I, j, k, they are taking unit vectors along the axis x, y, z as a suffix x, a suffix y, and a suffix z. So now, given the vector f is irrotational, we want to find what is the unknown constant c1, which is present in the given vector f. So let us use the condition given for the vector f. So what is the condition given about vector f? F vector is irrotational. So when do you say f vector is irrotational? When del cross f vector is equals 0 vector. So let us use the condition and find what is value of the unknown constant c1. So how will you find a del cross f vector? So using determinant operation. So the first row is always fixed. They are going to be components of, they are going to be unit vectors along the respective uh, variables. Okay. So here in the question it is given ax is a unit vector along x-axis, ay is the unit vector along y-axis, and az is the unit vector along z-axis. So therefore, in the first row, I'm filling up all the unit vectors ax, ay, az. In the second row, I'm going to fill the components of del. So what is ax component of del, which is dou by dou x, and then dou by dou y, and then dou by dou z, and then components of f vector. So 4y minus c1z, third row. 4x plus 2z and 2y plus z equals 0 vector. Now we can expand the determinant which is present on the left hand side. So usual determinant expansion. Suppose I am expanding with respect to first row. I'm going to find what are the minus of ax vector. Okay, minus of ax vector multiplied by ax. Okay, ax vector leaving first row and the first column. So we are going to have dou by dou y of 2y plus z minus dou by dou z of 4x plus 2z minus second term ay dou by dou x of 2y plus z minus dou by dou z of 4y minus c1z. Now the third one, leaving the first row and the third column, you are going to have az multiplied by dou by dou x of 4x plus 2z minus dou by dou y of 4y minus c1z. On the right hand side, we can expand the zero vector. So what is zero vector? Ith component is 0, jth component is 0, kth component is 0. So therefore, we are going to have 0 ax vector plus 0 ay vector plus 0 az vector. So you simplify the left hand side, simplify each component separately. So first one, differentiation of 2y plus z with respect to y. With respect to y, z becomes 0, 2y becomes 2 minus differentiation of 4x plus 2z partially with respect to z. So with respect to z, 4x becomes 0, 2z becomes 2. So therefore, the component of ax becomes 2 minus 2, which is 0. Coming to the component of ay, differentiation of 2y plus z partially with respect to x. I think there is no x term. So when I differentiate, the answer is 0. And minus differentiation of 4y minus c1z with respect to z. With respect to z, 4y becomes 0. And minus c1z becomes minus c1. So already I have negative outside, so it is going to be positive c1. And next one, component of az. Differentiate 4x plus 2z with respect to x. So with respect to x, 2z becomes 0, 4x becomes 4. And then minus differentiation of 4y minus c1z partially with respect to y. So when I differentiate partially with respect to y, c1z becomes 0, 4y becomes 4. So therefore, we are going to get az component as 4 minus 4. On the right hand side, we have 0 ax, 0 ay, 0 az. Now you simplify the left hand side. 0 ax So minus C1ay plus 0az equals 0ax plus 0ay plus 0az. Now we can do this simplification. You can find the C1 value by equating like components on both sides. So we have only one non-zero component on the left-hand side. So that is a component of ay. Component of ay is minus C1. On the right-hand side, the ay component is 0. So C1 value is 0. So therefore, we are able to find what is answer for the unknown constant C1. It is nothing but 0. Now let us solve the next problem. Consider the integration over c sin x dx by x square into x square plus 4, where c is a counterclockwise oriented circle defined as modulus of x minus I equals 2. What is the value of the integral? It is a multiple choice question. So given 4 choices. Choice A minus pi by 8 into sine 2i. Choice B pi by 8 into sine 2i. Choice C minus pi by 4 into sine 2i. Choice D pi by 4 into sine 2i. So this problem is an application of Cauchy's integral formula. Okay. Now let us understand the question. We are going to find what is integration over the closed curve. And the orientation of the closed curve is counterclockwise. Counterclockwise is nothing but anticlockwise. Anticlockwise is always considered as positive direction. What is the equation of the circle? It is given as modulus of x minus I equals 2. Now, to solve this, first of all, let us find what is the poles of the function f of x. But the term which is present inside the integration. Okay, f of x is sin x by x square into x square plus 4. So let us solve the problem by finding the poles. So how will you find poles of any function? By equating denominator to 0. So here the denominator of f of x is x square into x square plus 4 equals 0. So multiplication of two factors equals 0. Either first factor 0 or the second factor 0. By equating the first factor to 0, x square value is 0. So x value is 0 and 0. Second factor, x square plus 4 is equal 0. So x square value is minus 4, or I can say x value is plus 2y and minus 2y. So we are able to find three different poles. First one, x equal to 0, and the order of the pole is 2. And the second pole is x equals 2y. It is a simple pole, that is pole of order 1. And the third pole is x equals minus 2y. It is also a simple pole, that is pole of order 1. Now, in next step, we are going to check what are the poles which present inside the given circle. So to observe that, you take the circle equation. So what is C given? Circle equation is given as modulus of x minus I equals 2. Now let us check whether my first pole lies inside C or lies outside C. Okay. So to find that, you are going to substitute the particular pole on the left hand side of the circle equation. So therefore, you are going to get modulus of 0 minus I, which is modulus of minus I. Modulus of minus I is nothing but 1. And after substituting the pole value, the left hand side of the circle equation, we got answer 1. What is the radius? Radius is 2. So by comparison, I can say the radius is bigger. Okay, so therefore the conclusion is the pole what we have taken is present inside the circle C. So x equals 0 is a pole of order 2 which lies inside C. Let us take the next pole. X equals 2y. The same procedure. You substitute x value on the left hand side of the circle equation. So you're going to get modulus of 2i minus I. So 2i minus I is I. Modulus of I is 1. Compare with the radius of the circle. Radius of circle is 2, whereas the left hand side of the circle equation, we got 1 after substituting the pole. So 1 is less than 2. So the conclusion is the pole lies inside the circle and it is of order 1. Let us take the next pole. X equals minus 2a. The same procedure. You substitute on the left hand side of the circle equation. So modulus of minus 2i minus I, which is modulus of minus 3i. Modulus of minus 3i is simply 3. And you compare this answer with the radius of the circle. So radius of circle is 2, whereas the value what we got is 3, which is greater than 2. So therefore, my conclusion is the pole x equals minus 2i lies outside the circle C. So we have given conclusion for all the three poles. Now we are going to consider what are the pole lies inside C. So for those poles, we are going to find residue. So we are going to find residue. Let us recall the formula for residue. So residue of the function f of x at the pole x equals a of order m is given by 1 minus 1 by m minus 1 factorial limit x approaches a d power m minus 1 by dx power m minus 1 x minus a power m into f of x. Now let us find residue for the first pole which lies inside C. So the first pole lies inside C is x equal to 0. So that is a value is 0 and m value is 2. It is of order 2. So let us substitute all these values. So I'm going to call the first residue as r suffix 1. 1 by 2 minus 1 factorial limit x approaches 0 d power m is 1. So 2. m minus 1 is 1. So d by dx of x minus 0 whole power m value is 2 x square. And f of x is sin x by x square into x square plus 4. So x square gets cancels. Now we are going to simplify what is differentiation of sin x by x square plus 4. Okay, before applying the limits. Now outside the limit we have factorial, that is 1 by 2 minus 1 factorial. 2 minus 1 factorial is 1 factorial and limit x approaches 0. We are going to appeal u by v rule because we have numerator by denominator form. Yes, both the numerator and denominator contains x. Okay, so when I apply u by v rule, my denominator becomes x square plus 4 the whole square. Numerator x square plus 4 into differentiation of sin x, which is cos x. Minus in the formula, numerator is constant, differentiate denominator. That is minus sin x. Differentiation of x square plus 4 is 2x. Now we can apply the limit. Okay, that is replace all the x value by 0. So therefore, I'm going to get 4 times of cos 0 minus 0 divided by 4 square. So cos 0 is 1. So we'll get 4 in the numerator and denominator is 4 square. Now we can simplify. So first residue is 1 by 4. Let us find the second residue, r suffix 2. So that is we are going to find residue for the pole x equals 2i of order 1. Okay, the same formula. A value is 2i, m value is 1. So therefore, the formula becomes, residue formula becomes limit x approaches 2i, x minus 2i into sin x divided by x square. Now you factorize x square plus 4 using the two poles, x plus 2i and x minus 2i. Now x minus 2i gets cancelled. Now for the remaining terms, we are going to replace x value by 2i. So therefore, numerator becomes sin 2i, denominator becomes 2i square into 2i plus 2i. So numerator is sin 2i, denominator 2i square is nothing but 4i square. 2i plus 2i is 4i. Again, you simplify. Denominator I square is minus 1. So denominator is minus 16i. Numerator is sin 2i. Now, if you want a further simplification, you can convert minus 1 as I square. So therefore, your R2 becomes I square sin 2i by 16i. Now, I cancel with I square in the numerator. So you'll get I sin 2i by 16. So now you can add both the residues, sum of the residues, which is 1 by 4 plus I sin 2i by 16. Now you take LCM and find the answer, sum of the residues. So LCM will be 16. So therefore, the first term numerator becomes 4. Second term, I sin 2i divided by common denominator 16. Now we are going to appeal the Cauchy residue theorem. By Cauchy residue theorem, the answer for the single integration over C sin x dx by x square and x square plus 4 is 2 pi I into sum of the residues. Sum of the residue here is sum of the two residues, R1 plus R2. So you just substitute the value 2 pi I into 4 by 16 plus I sin 2i by 16. Now we can do the simplification. You multiply 2 pi I for each term separately. So your first term 2 pi I into 4 by 16 plus 2 pi I into sin 2i by 16. Now numerator first term 2 into 4 8 cancel with the 16 two times. So your first term becomes pi I by 2. Second term I square is minus 1. So we have minus pi sin 2i, 2 cancel with the 16. So minus pi sin 2i by 8. So which is the final answer. Hope you understood the last problem. Now let us move to the next equation. The next equation is taken from vector calculus. The vector function f of r is given minus xi plus yj is defined over a closed arc shown in the figure. What is the line integral of integration over C f of r dot dr? And it is a multiple choice question. We have 4 options: 1 by 2, 1 by 4, 1 by 6, and 1 by 3. Now, first of all, we'll try to check, because the given integration is a single integration. We try to check whether we can apply Green's theorem or Stokes theorem. Okay, we know that Stokes theorem will be effective for the 3-dimensional object. Now it is given 2 dimension. So we are going to check whether Green's theorem is applicable here or not. Okay, and please remember, Green's theorem is always applicable for the closed curve. So here it is not a closed arc actually. It is not a closed curve. It is just a portion of a circle, that is circular arc. So now we are going to work out the integration directly. We cannot use any theorems. Okay, now f of r is given as minus xi plus yj, and dr is given as dxi plus dyj. Now you find out f of r dot dr. F of r is a vector, dr is a vector. So multiply two vectors using dot product, component wise multiplication. So you are going to get minus x dx plus y dy. Now let us take the given integration. Integration over C f of r dot dr equals integration over C. Let us substitute the value. Okay, minus x dx plus y dy. Now this is single integration involving two variables. So we cannot, we want to convert the two variable into single variable. Okay, so I'm going to appeal Cartesian to polar form. So C is a circular arc. Okay. So we know that Cartesian to polar conversion, x equals r cos theta and y equals r sin theta. Yes, but here the radius of circle is 1. So therefore your x is cos theta, y is sin theta. And theta varies from 0 to pi by 4 because we are taking only the circular arc between 0 to pi by 4. Okay, portion. It is given in the diagram. Now let us find dx and dy. So dx will be minus sin theta d theta, dy will be cos theta d theta. Now let us substitute x value, y value, dx value, dy value, and limits in the above integration. So therefore, your integration over C minus x dx plus y dy, it becomes integration between 0 to pi by 4 minus x value is cos theta, minus cos theta into dx is minus sin theta d theta. Second term plus y is sin theta, dy is cos theta d theta. Now let us simplify. So the first term becomes plus cos theta sin theta d theta. Second term is also plus cos theta sin theta d theta. So it is going to be 2 times of sin theta cos theta d theta. Integration between 0 to pi by 4. Now you cannot integrate the term directly. So therefore, I'm going to use the trigonometric formula. We know that 2 sin theta into cos theta is sin 2 theta. So therefore, the above integration becomes integration 0 to pi by 4 sin 2 theta by d theta. Now we can integrate sin 2 theta. Integration of sin function is minus cos function. Minus cos 2 theta divided by differentiation of 2 theta, which is 2. Now let us substitute the limit. Integration is completed. Lower limit is 0, upper limit is pi by 4. So you start substituting the upper limit. So before substituting the upper limit, let us remove the constant denominator outside. So minus 1 by 2. So cos 2 into upper limit theta value is replaced by pi by 4. So cos 2 into pi by 4 minus lower limit cos 0. So now 2 cancel with the 4, you will get cos pi by 2 minus cos 0. Cos pi by 2 is nothing but cos 90. We know that cos 90 value is 0 and cos 0 value is 1. So therefore, minus 1 by 2 into minus 1 is plus 1 by 2, which is given in option A. So for the given problem, option A is the correct answer. Let us move to the next question. Next question is also from vector calculus. Consider the integral. Integration over C, x dy minus y dx. The line integration being taken in a counterclockwise direction over the closed curve capital C that forms the boundary of the region R shown in the given figure. Okay. The region R is a area enclosed by union of a 2 by 3 rectangle and a semicircle of radius 1. what is the value of the line integration. Okay, so whenever a single integration is given over a closed curve, we can always try to apply the Green's theorem. Okay, now here the closed curve C is not given in terms of equation; it is given in terms of pictorial representation or a graph. Okay, it is given as graph. Okay, so the closed curve C, it is formed by boundary of the two regions. Okay, it is having two different curves. So first one is rectangular and then a portion of a circle. Okay, and the rectangle area is 2 by 3 and the semicircle of radius 1. Okay, you can refer the diagram. It is a multiple choice question and the options are given as A 6 plus pi by 2 and B 8 plus pi, C 12 plus pi and D 16 plus 2 pi. Now clearly you can see R, the given region R bounded by the simple closed curve. Okay, so what are the closed curve? It is a rectangle of area 2 by 3 and a semicircle of radius 1. Okay, let us try to employ the Green's theorem. So integration over C m dx plus n dy equals double integration over R dou n by dou x minus dou m by dou y into dx dy. Now you compare left hand side of the Green's theorem with the given single integration and try to find out what is your m value and n value. So please be careful when you find what is capital M and capital N. Please always remember your capital M is coefficient of dx in the single integration, so which is given as minus y, and your capital N is coefficient of dy, which is given as x. So from capital M, you find dou m by dou y. And from capital N, you find out dou n by dou x. So therefore, dou m by dou y is minus 1, dou n by dou x is plus 1. So find out dou n by dou x minus dou m by dou y. So which is 1 minus of minus 1, which is 2. So therefore, the answer for the given single integration over C, x dy minus y dx equals double integration over R, substitute the values 2 times of dx dy. Let us take 2 outside the integration because it is constant present in multiplication. Now we have 2 times double integration over R 2x d 2 the double integration over R dx dy. Now what is double integration over R dx dy? It is nothing but area of R. So what is R? R is formed by two different regions. Okay, rectangle and the semicircle. So therefore we are going to sum up the areas of rectangle and the area of semicircle. Okay, so it is 2 times area of rectangle and area of rectangle, okay, length 2, breadth 3, so 2 into 3, and the area of semicircle, we know that the area of semicircle is pi r square by 2. Okay, so pi by 2 into r square, r value is 1. Okay, it is pi by 2 into 1 square. So when you simplify, you are going to get 6 plus 2 into 6 plus pi by 2. Let us take LCM. So if you take LCM, you are going to get 2 times of 12 plus pi by 2. So 2 and 1 by 2 gets cancelled. So your answer is 12 plus pi. So therefore, the answer for the given single integration is 12 plus pi, which is nothing but your option C. Let us solve the fifth problem. Okay. An integral capital I over a counterclockwise circle capital C is given by capital I equals integration over C z square minus 1 by z square plus 1 into e power z dz. If capital C is defined as modulus of z equals 3, then the value of I is what? Okay, we have 4 options, multiple choice question. So first option, minus pi I into sine 1, option B, minus 2 pi I into sine 1, option C, minus 3 pi I into sine 1, option D, minus 4 pi I into sine 1. Okay, so this problem is taken from complex analysis, especially from complex integration. So whenever a complex integration is given, immediately you have to think of Cauchy integral formula or Cauchy's residue theorem. So for simplicity, I'm going to work out the integration using Cauchy's residue theorem. So to apply Cauchy's residue theorem, first of all, you write what are the terms present inside the integration. Okay, so we are going to call it as f of z. F of z is given by z square minus 1 divided by z square plus 1 numerator is multiplied by e power z. Now let us start finding the poles of f of z. So by equating denominator of f of z to 0, z square plus 1 equals 0, z square value is minus 1, or I can say z value is plus or minus I. So z equals I and z equals minus I, they are simple poles. Now let us see what are the pole lies inside C. So to find that, we are going to take the given circle equation. So what is the circle equation given? Modulus of z equals 3. So let us substitute the first pole z equals minus plus I in the circle, left hand side of circle equation. Modulus of I is 1. 1 compare with the radius of the circle 3. So radius of circle is bigger. So your conclusion is the pole lies inside the circle. So let us take the second pole, z equals minus I. Same process, substitute z value on the left hand side of circle equation. You are going to get modulus of minus I. Modulus of minus of I is also plus 1. Compare with the radius of the circle. So 1 less than 3. Radius is bigger. The value of the pole is smaller. So therefore, the conclusion is the pole z equals minus I also lies inside C. So therefore, we need to find a residue for those poles which present inside the closed curve C. So let us find out residue for the first pole. R1, I'm going to call it as R1. So the formula is limit z approaches I, z minus I into f of z. F of z is z square minus 1 into e power z. Denominator of f of z, you always try to write in terms of factors using the poles. So z plus I into z minus I. Now we can simplify. Z minus I gets cancelled. Right? Now we can apply the limit. Replace all the z value by I. So therefore, your numerator becomes I square minus 1 into e power I. Denominator becomes I plus I. Let us simplify again. So I square minus 1 into e power I. Denominator I plus I becomes 2I. Now numerator I square is minus 1. Minus 1 into, sorry, minus 1 is minus 2. So numerator is minus 2 e power I. Denominator is 2I. So 2 and 2 gets cancels. So therefore, your first residue is minus e power I by I. Let us find the residue for the second pole. We call it as R suffix 2. Limit z approaches minus I, z plus I multiplied by f of z. Z square minus 1 into e power z, as usual, denominator of f of z, you write in terms of factors using, poles. Z plus I into z minus I. Z plus I gets cancels. Now we can apply limit. Replace all the z value by minus I. So your numerator becomes minus I square minus 1 into e power minus I. Denominator minus I. So simplify the numerator and denominator further. So your denominator becomes minus 2I. Numerator minus I square is minus 1. Minus 1 minus 1 is minus 2. Minus 2 into e power minus I. So minus 2 minus 2 gets cancels. We have e power minus I by I. Find the sum of the residues R1 plus R2, which is given by minus e power I by I plus e power minus I by I. Now we can remove the common factor outside and remove the negative sign outside. So we have minus 1 by I, minus e power I becomes plus e power I, plus e power minus I becomes minus e power minus I. Now we know that e power I theta minus e power minus I theta is nothing but two I sin theta. Yes. So therefore, your term e power I theta minus e power minus I becomes a 2I into sine 1. So now 1 by I cancel with I. So therefore, the final answer for sum of the residues is minus 2 into sine 1. So let us use the sum of the residue in Cauchy's theorem, residue theorem, to find the answer for the single integration. So the given single integration is I equals integration over C z square minus 1 into e power z divided by z square plus 1 into dz equals 2 pi I into R1 plus R2, which is sum of the residues. So therefore, it is 2 pi I into minus 2 sine 1, which is minus 4 pi into sine 1. So which is exactly option D. So therefore, the answer for the uh, problem is option D. Let us work out a problem based on vector calculus. If the vector function f vector equals ax cap into 3y minus k1z plus ay cap k2x minus 2z minus az cap k3y plus z is irrotational, then the value of the constants k1, k2, k3 respectively are, it is a multiple choice question. So we have four options. So we have to pick the correct option. Now let us use the condition given about f vector. F vector is irrotational. So what is conditional for irrotational vector? F vector is irrotational means I can say del cross f vector is equals 0 vector. So let us expand what is del cross f vector. Del cross f vector is a determinant. First row is going to be ax cap, ay cap, az cap, which are unit vectors. Okay. And second row is going to be components of del, dou by dou x, dou by dou y, dou by dou z. And third row, it is going to be components of the given f vector. So which is a 3y minus k1z, k2x minus 2z minus k3y plus z. Now let us expand the determinant in the usual way. Okay. So expanding with respect to first row, ax cap. Okay, leaving first row and the first column. So it is dou by dou y of minus k3y plus z minus dou by dou z of k2x minus 2z. And then minus ay cap, leaving first row and the second column. So we have dou by dou x of minus k3y plus z minus dou by dou z of 3y minus k1z plus az cap, leaving first row and the third column. So we have dou by dou x of k2x minus 2z minus dou by dou y of 3y minus k1z. On the right hand side, expanding 0 vector is 0 ax cap plus 0 ay cap plus 0 az cap. So you simplify the left hand side. Okay, you are going to simplify the components by performing the partial derivatives, simplification of partial derivatives. So let us simplify the ax cap component. So differentiation of minus k3y plus z with respect to y partially. With respect to y partially, z becomes 0, minus k3y becomes minus k3. And then differentiation of k2x minus 2z with respect to z partially. With respect to z partially, k2x becomes 0 and minus 2z becomes minus 2. Already I have negative, so it becomes plus 2. So it is minus k3 plus 2. And component of ay cap. So differentiation of minus k3y plus z with respect to x. There is no x term, answer is 0. And then differentiation of 3y minus k1z partially with respect to z. So you are going to get a 3y 0, 3y as 0, minus k1z becomes minus k1 multiplied by negative, which is plus k1. So therefore your ay cap component is minus k1. And component of az cap, dou by dou x of k2x minus 2z. So you're going to get a k2 and 3y minus k1z. You're going to differentiate with respect to y partially. So therefore, you'll get a 3 minus 0, which is minus 3 actually. Now we can equate the like components on both sides. That is ax cap component equated with ax cap component likewise. Okay. So on the left hand side, component of ax cap is minus k3 plus 2. And component of ay is k1 on the left hand side, 0 on the right hand side. And az cap, left hand side k2 minus 3, right hand side 0. So from this here, k1 value is 0, k2 value is 3.0, k3 value is plus 2. So which exactly matches the option C, option B given. Now let us solve one more simple problem from complex analysis. What are the modulus R and the argument theta of the complex number 3 plus 4? It is very simple problem, and it is a multiple choice question. We have four options. So we want to select the correct option. So let us start with the formula for modulus and argument theta. So modulus R of any complex number z equals x plus iy is given by R equals root of x square plus y square, and argument of any complex number z equals x plus iy is given as theta equals tan inverse of y by x. Okay, let us find what is R value. So it is root of 3 square plus 4 square, which is root of 9 plus 16, which is root 25, which is 5. And the argument of z, which is given by theta equals tan inverse of y is 4 and z is x is 3. So tan inverse of 4 by 3. So theta is tan inverse of 4 by 3. And r value is 5. That is your modulus is 5 and your argument is tan inverse of 4 by 3, which matches option D. Let us solve the next equation. The value of the integral, integration over c 2z plus 5 into dz divided by z minus 1 by 2 into z square minus 4z plus 5 over the contour modulus of z equals 1 taken in the anti-clockwise direction would be what? Multiple choice question. So we have 4 options. We have to pick the correct choice. Now this is a problem of complex integration over the closed curve. Especially it is a circle. So we try to apply the Cauchy residue theorem. So to apply Cauchy residue theorem, let us write what is f of z, which is 2z plus 5 divided by z minus 1 by 2 into z square minus 4z plus 5. So let us find poles of f of z by equating denominator of f of z to 0. So z minus 1 by 2 into z square minus 4z plus 5 equals 0. So solving first factor, z value is 1 by 2. Solving second factor using the formula, we know that any quadratic equation az square plus bz plus c equals 0, whose solution is given by z equals minus b plus or minus root of b square minus 4ac by 2a. So therefore, a z value is minus of minus 4 plus or minus root of minus 4 square minus 4 into 1 into 5 divided by 2 into 1. So therefore, z value is 1 by 2 and the second z value 4 plus or minus root of 16 minus 20 by 2. So which is 4 plus or minus root 4 by 2, which is 4 plus or minus. We know that square root of negative number is plus or minus I. So plus or minus I into root of 4 is 2. 4 plus or minus 2i by 2. Now from the numerator, 2 will be the common factor. You pull it outside. Excuse me. 2 times of 2 plus or minus I divided by 2. So 2 and 2 gets cancels. So therefore, the poles of f of z are z equals 1 by 2, z equals 2 plus I, z equals 2 minus I. And all the poles are having order 1 or simple pole. They are called simple pole. Now next one, we want to check what are the poles lies inside C. For those poles, you are going to find residues. So how to check whether a particular pole lies inside C or outside C? You just take the given circle equation. So the circle equation given is modulus of z equals 1. So let us substitute the first pole. Let us check whether first pole lies inside C. So modulus of z equals 1, substitute z value, modulus of 1 by 2, which is 1 by 2, compare with the radius given, which is 1. 1 by 2 is less than 1, radius is bigger. So the pole z equals 1 by 2 lies inside C. Let us take the second pole, z equals 2 plus I. Take the same circle equation, substitute on the left-hand side, z value is 2 plus I. You are going to get modulus of 2 plus I, which is root of 2 square plus 1 square, which is root 5. And root 5 is definitely greater than the radius of the circle, which is 1. So therefore, the pole z equals 2 plus I lies outside C. Finally, you take the third pole, z equals 2 minus I. Again, substitute in the same circle equation. And substituting your left-hand side of circle equation, modulus of 2 minus I equals root of 2 square plus 1 square, again root 5 greater than 1. So the pole lies outside. Now we have only one pole which lies inside C, that is z equals 1 by 2, and it is a simple pole, that is pole of order 1. So let us find residue for that single pole. R1, limit z approaches 1 by 2, z minus 1 by 2 into f of z, 2z plus 5 into z minus 1 by 2 into z square minus 4z plus 5. Now z minus 1 by 2, z minus 1 by 2 gets cancels. Now you can apply limit. That is replace all the z value by 1 by 2. So therefore, you are going to get 2 times of 1 by 2 plus 5. So 2 times of 1 by 2 is 1. 1 plus 5 divided by denominator. 1 by 2 square minus 4 into 1 by 2 plus 5. So denominator becomes 1 by 4 minus 2 plus 5. Now simplify numerator and denominator. Numerator 1 plus 5 is 6. Denominator minus 2 plus 5 is plus 3. 1 by 4 plus 3. Simplify denominator again. You do the cross multiplication, you will get 12 plus 1 by 4, which is 13 by 4 in the denominator. Numerator is 6. So now 6 into 4 is 24 by 13. So the answer is 24 by 13, which is nothing but option C. So let us solve the ninth problem. So consider the function f of z equals z plus z star, where z is a complex variable and z star denotes its complex conjugate. Which one of the following is true? So we have 4 choices. First statement, F of z is both continuous and analytic. Second choice, f of z is continuous but not analytic. Third choice, f of z is not continuous but it is analytic. Fourth choice, f of z is neither continuous nor analytic. That is, we are going to check continuity and analyticity for the given function f of z. So what is f of z? It is z plus z star. We know that z is x plus iy and z star is conjugate of x plus iy, which is x minus iy. So therefore, z plus z star becomes 2x. Now we know that f of z is u plus iv. So therefore, equating real part, you're going to get u value 2x. Equating imaginary part, p value is 0. Now let us find the partial derivative ux, uy, vx, vy. Ux becomes 2, uy is 0, vx 0, vy 0. Now let's check the CR equation. Ux is 2, Vy is 0, 2 cannot be equal to 0. So CR equation is not satisfied. So therefore, the given function is not analytic. Okay. And you can see the option clearly. The first option is ruled out because it is given f of z is analytic. And the third option is also ruled out because it is given as analytic. Now let us check whether f of z is continuous or discontinuous. So clearly f of z equals 2x. 2x is a polynomial and we know that every polynomial is a continuous function. So therefore f of z is continuous and it is not analytic. So which is given in the second option. F of z is continuous but it is not analytic. So let us solve the 10th problem. In the neighborhood of z equals 1, the function f of z has a power series expansion of the form f of z equals 1 plus 1 minus z plus 1 minus z the whole square plus etc. Then f of z is what? So a series expansion is given. We want to find what is the function, corresponding function. Okay, and given it is a Taylor series expansion. Okay, the power series expansion because it contains okay, it is a power series expansion in the neighborhood of z equals 1. Okay, now we can apply the formula directly. You just compare the given series with 1 plus x square plus etc. up to infinity. So we know that the answer for this series is given by 1 minus x whole power minus 1. So here your x value is 1 minus z. So which is 1 minus z power minus 1, which on simplification gives z power minus 1. Z power minus 1 is nothing but 1 by z. And it is a multiple choice question. So 1 by z is present in option A. So therefore, the answer for the problem 10 is option A, 1 by z. So with this, we are coming to the conclusion of today's class. Thank you for your listening. Thank you, students.